Hi everyone, Ryan here again. In this video, we're going to talk about how to optimize Dana, DNA area NETosis analysis, and this is going to allow you to use it for different cell types, different species, and different stains. I'm going to show you how Dana was optimized to DAPI stained mouse neutrophil images. Before we begin, you're going to need to have installed Dana previously, and this means that if you open up Fiji, you have the two Dana macros available from the plugins pull-down menu, and you are also able to run the Dana 2 executable file. Okay, so to optimize Dana, we're going to need 15 images that are representative of our sample. I've gone ahead and selected 15 images here. You're going to need to do the same thing for your sample, and we can go ahead and just open these images up in Fiji. We're also going to want to open the optimization spreadsheet for Dana, and to do that we simply go back to our Dana folder and we select the optimization updated spreadsheet. Okay, so this spreadsheet, I've gone ahead and entered all the names of the images that I'm going to be analyzing. It contains 3 tabs: the image counts tab, upper cutoff optimization, and net cutoff optimization. And once you enter in the image names over here, it will automatically propagate to these other 2 tabs. So the first thing we're going to want to do in optimizing these images is effectively go through each one and count these cells by eye. And we're going to count the total number of cells, the total number of nets, and then any multiples that we notice within the image. I'm going to perform these counts on the first image so you get an idea of how to do it. Okay, so the first thing that I want to do is, because these are in blue on black, it's a little bit hard to see. So I'm going to go ahead and change the type of this image to an 8-bit image. This just means it turns it to grayscale. The next thing I'm going to do is adjust the brightness and contrast to make it a little bit easier to pick up. Okay, so now I'm going to go through the image and count by eye. So the first thing I'm going to do is count just the total number of cells. 1, 2, 3, 4, 5, 6, 7. Of note, if a cell is touching the edge of the image, I don't count it, because Dana doesn't either. So we have 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So I count 31 total cells. So this is TNF LPS1, so that's 31. Looking at the total number of nets, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19, and 20. I'll say 20 total nets in this image. Counting multiples is a little bit harder by eye, so what I've been doing is I've been adjusting the brightness back to normal, and then I've been running Dana Part 1 on this. And once the ROIs are placed on the image, it's relatively easy to see when you have single cells, or multiple cells grouped in a single ROI. For instance, 5 is a multiple here. Let's see. Looks like primarily 5 is the only multiple that I'm picking up on this image. So I can go back to the Excel spreadsheet and just enter 1 for multiples. Of note that when you have 1 multiple, in this case it was 2 cells, so your total cell number also decreased by 2, so that goes down to 29. I'm going to go ahead and do this same process for the rest of these images, so we can speed this up. Okay, so now we have the counts for all of our images. The next thing we're going to do is make sure that we've run Dana Part 1 on all of these images. So I'm just going to go ahead and do that really quickly through the batch processing mode. Plugins, Dana 1 batch. I've stored all of the images that I'm analyzing in this mouse neutrophil DAPI folder on my desktop, so I'm going to select that. It's going to output all of these files for me here. And in the next part, we're basically going to look at how to get our different cutoff parameters, more specifically the upper and the lower, as well as the net cutoff. To find these cutoffs, we're going to be using Dana Part 2, so I'm going to go ahead and open that. The values that we're initially going to be concerned with are the upper elimination cutoff parameter and this lower cutoff value. So looking at our optimization sheet, we're first going to look at this value right here, which represents the upper elimination cutoff parameter. Basically, Dana Part 2 excludes ROIs that are above this threshold. So whatever your mean raw integrated density is, plus 1.2 times the standard deviation of that raw integrated density. The 1.2 is what we're trying to optimize, whether we want to use 1.2, 1.5, 1.8, or 2.1, or even something in the middle to best exclude the multiples from the rest of our data set. To start, we're going to use this 1.2 times the standard deviation for our upper elimination cutoff parameter. So I'm going to change that to 1.2. We also want to make sure our input and output directories are correct. Mine's not at the moment, so I will change that really fast. Dana 1, Dana 2. Okay. So now that we have this set for 1.2, I'm going to go ahead and run Dana. Oops, and you must, yeah. So I want to normalize to the mean area of the 5 smallest non-outlier ROIs. Okay. So run Dana. And we have our Dana 2 output. The first thing I'm going to look at is this summary.csv file. During optimization, this summary.csv file is going to tell us a lot about whether our lower cutoff parameter is set optimally. So down here we have this box. Basically it says, do we want to consider optimizing the lower parameter? The answer is yes. And this propagates yes when when the sample that we just ran Dana Part 2 on contains over 20 fragments or more. And when it does, it indicates that we might not have the parameter set low enough because we really don't expect to see that many fragments in a given sample set. The summary.csv file also contains a list of files to check. So we have 3 here. And basically this is listed from the file with the most fragments. These file names provide a good place to start to set our lower cutoff parameter. So the first one we have is 89206. So I'm going to go ahead and open up that image, as well as the file from our Dana 2 output, 89206, untreated 5 blue. 89206, untreated 5 blue. So when I open this image, it has 16 fragments, so that's pretty high. And then I will open the actual image, untreated 5 blue. So when I run Dana Part 1 on this, okay, this is picking up a fragment on cell number 20. I can toggle my ROI manager on and off. So cell 20 is right over here. So do I think that's a fragment? Yes, I do. I can also make this a little bit easier to see by changing it again to 8-bit and then adjusting the brightness. Okay. So 20 I would agree with is a fragment. I also have a lot down here towards this end. 73 through 76 have all been labeled as fragments. 73, I would say that's probably not a fragment. And the raw integrated density on 73 is around 9,500. So 73, 74, 75 I would say is definitely not a fragment either. 74 doesn't appear to be a fragment. And then 70, 76 is down in the corner. That one might be a fragment. That one's around 8,500. So based on this, it seems like things as low as 9,500, or with things as low as a raw integrated density of 9,500, may in fact be cells. So the next time when I run Dana Part 2 again, I'm going to go ahead and change my lower cutoff parameter to 9,500 instead of 20,000. And you can basically go ahead and do this for all of the images that are listed. For all of the images that are listed in the summary.csv file to make sure that your lower cutoff parameter accurately captures the data you see. but we're just going to start with 9500 and progress from there. So now I'm going to go ahead and close any output files that I have open. So I have 89206 open right here. And then with my new lower cutoff value, I'm going to go and run Dana again. And after you run Dana, all of this output will be updated. So I can click on the same summary file, and it's going to show me, do I still want to consider reoptimizing? Yes. And then it gives me these list of images as before. So I'm going to go ahead and optimize, or I'm going to go ahead and open 75549 TNF-LPS2, 75549 TNF-LPS2. Okay, so this is, it's giving me a decent number of 4 fragments, so I can open that actual image to, let's see, 75549 TNF-LPS2. Okay, so I will run Dana on this. It's going to fit that. Image type, I'm going to change to 8-bit. Adjust the brightness. Okay, so let's look at what we have here. So I clearly see 1, 2, 3, 4, 5, 6 cells, and that includes one that's labeled as a multiple, number 8 right here. And then the ones labeled as fragments are going to be 3 and 4, which I would agree with, as well as 6 and 7, which I would also agree with. So I think Dana did a good job eliminating the fragments on these. So I'm going to exit out of this image, and then I'm going to open up one of the other ones available, 89206, untreated 5 blue. So that was the same one we were looking at before. So I'll open that up, run Dana part 1, and then I will open, where did it go? Dana 2 output, untreated 5 blue, and we can look and see if this did a better job this time. So it looks like it labeled 3 cells as fragments in this image, so not too many. And that includes 76, which we agreed was a fragment before. I'll adjust this to make it easier to view. Okay. So 76 is down in the corner here. I would agree that's a fragment. And we have 73. That was one of the ones I think we thought was a fragment before, and since we set a cutoff at 9500, 9486 is going to get excluded, so we can lower our cutoff slightly to reflect that. And then the last one was 20, which I think we also agreed was a cutoff before, or was an outlier before. And 20, yeah, it was just this one right here. So I would still agree that that is a fragment. So I think that Dana did a pretty good job overall. We can change this to 9450 though, so we capture that cell down here. But this is probably a good lower cutoff parameter that I would stick with for the analysis of the rest of my images. And of note that when you optimize, your lower cutoff parameter shouldn't really change after that, even if you're running it on other samples and it's suggesting that you lower your or that you optimize your cutoff parameter further. Once you pick a lower cutoff parameter, you should use it on all of your images and not change it at all. Since we're happy with our lower cutoff parameter now, we're going to go ahead and do the upper cutoff parameter. So I'm going to go ahead and close this image, and I can close all these associated Fiji tabs. And then based on our new lower cutoff parameter, I'm going to open the, I'm going to exit out of this real quick, and then open the optimization spreadsheet. And I'm in the upper cutoff optimization tab. So I'm going to start with this first one, this first value right here, 1.2. So I have that entered for my upper elimination cutoff parameter. I'm then going to run Dana. And I have my Dana 2 output. I'm going to go to the first image. And all I'm going to do for this now is basically take the number of multiples, which is 6, and enter it right here. And I'm going to do this for all of the images, all the way down the line. And it's going to calculate the absolute difference. So basically the fragments I've seen by eye it's the absolute value of the fragments I've seen by eye subtracted from the multiples that the program picks up. So I'm going to do this for all of the images with the 1.2 cutoff. Then I'm going to go through and change this to the next value, which is 1.5. So I'll change it to 1.5 and then run Dana again. and then go through, open the file again. This time it's picked up 4 multiples. Oops, over here. So I'm going to go through and propagate this for every cutoff for every image. And I'll rejoin you once I've done that for all of them. Okay, so once these values have been generated for each different cutoff in here, we can look at the average down below, and we want to select the value at the, or we want to select the average, the lowest average. So it looks like 1.8 and 2.1 standard deviations gave us about the same. They both gave an average of 0.86 for an absolute difference. And I'm going to select the value somewhere in between that. I'm going to choose 2.0 as my cutoff. Okay. So now I will go back to the Dana plugin, switch this upper elimination cutoff parameter to 2.0, and then we can proceed with the next part of the analysis, which is the net cutoff. To determine the net cutoff, we're going to go through a similar process. So I'm going to open the optimization spreadsheet and navigate to the net cutoff optimization tab. And this time, instead of changing the upper elimination cutoff parameter and looking at the values, we're going to change these DNA decondensation cutoffs. And we have these values shown right here, 3 times ranging to 12 times. And we have several of them laid out initially, 3, 4, 5, and 6. So I'm just going to run Dana using my upper elimination cutoff parameter we set, as well as the lower cutoff value we set. I'm then going to go ahead and look at the output that's been generated. So for the first image, 75546 TNF-LPS1 blue, I'm going to open that up, and I'm going to scroll over, and I'm going to look at the number of cells greater than 3 times, 4 times, 5 times, and 6 times. And I'm just going to enter these values in here. So 18, 15, 10, 6. And I'm going to do that for all of these images. And once that's complete, all I'm simply going to do is I'm going to repeat the same process with 7, 8, 10, and 12, and just change those values in here. So this would be 7, this would be 8, this would be 10, and this would be 12. And I'm just going to run Dana again and then fill in all of these values. I'm going to skip ahead a little bit and just propagate all of those values for you, and then I will show you how to do the last part of optimizing Dana. Now that we've generated all these values, we can go and determine our net cutoff. So how this works is we're basically going to pick the net cutoff based on what we saw by eye and what Dana was able to pick up. So for this first image, we picked up 20 nets by eye, and the cutoff that best captures that in Dana is this 3 times cutoff. So I'm just going to write 3 right here. It's going to propagate a weighted average, which is basically the cutoff times the number of cells. And I'm going to do this for each image down the line. So this time I saw 6 nets. 10x cutoff was the best. And this time I saw 7 nets. That looks to be around the 6 times cutoff being the best. This one I saw 0 nets. In this case, I'm always going to choose the first 0. So in this times it's 10. And we're just going to go through down the line and basically choose all of these. So 0, that one would be the 3 cutoff. This one is also 0, that would be the 4 cutoff. And then this one is 1, that would be the 5 cutoff. We're basically just choosing the cutoff that most accurately represents our data. So this is 16, so it's closest to 4x. This one is 0. I would choose the 5 one because it's the first 0. This one's also 0. 4 again. This one's 5 nets, and that's the closest to the 7 cutoff. 10 nets. That one's closest to 7 again. This one has 0 nets, and that is the 10x cutoff. This one is 3 nets, and that's between 5 and 6, so I can do 5.5. It doesn't have to be exact. And this one's 0, so I would choose again the first 0, which is 8. So that gives me a net cutoff of 5.3 times. Now that we have our net cutoff of 5.3 times, we can enter this back into our Dana. So this becomes 5.3 And what I would go ahead and do is, now that you have it optimized, you have the correct input-output directory, you have your upper elimination cutoff parameter, your lower cutoff value, as well as your net cutoff parameter, I would go ahead and save your current settings. And you can choose where you want to save them. I'm just going to go ahead and put them in my Dana folder that I've saved on my desktop. And there's this Dana settings folder here. And then you can just label this. So this would be Dappy Mouse Neutrophil. That way, you can always go back, especially if you're doing different cell types or different stains, and you can access the parameters that you used before. I would also save the optimization spreadsheet, so you can go back and look to see how you got the cutoff parameters that you did. And that concludes the tutorial on how to optimize Dana. Thank you for listening.